Good morning and welcome to this morning's keynote lecture. I'm Omar Kniao, Professor of Applied Mathematics and Computational Science, Chair of the 2018 Enrichment Program. It is my pleasure to introduce today's speaker, Professor Carlo Ratti of MIT. Carlo is Professor of Urban Technologies and Planning at MIT, where he directs the Senseable City Laboratory. He is an architect and engineer by training and is a founding partner of the international design and innovation practice, Carlo Ratti Associati. He has co-authored over 500 publications and holds several patents. His work has been exhibited worldwide at venues such as the Venice Biennale, the Design Museum in Barcelona, the Science Museum in London, and the Museum of Modern Art in New York. Two of his projects, the Digital Water Pavilion and the Copenhagen Wheel, have been included by Time magazine in the list of best innovations of the year. His work has won a number of accolades, including being featured in Esquire's Best and Brightest, in Wired magazine's Smart List. Blueprint magazine included him in the 25 people who will change the world of design, and Fast Company named him as one of the 50 most influential designers in America. He is currently serving as co-chair of the World Economic Forum's Global Future Councils on Cities and Urbanization, and as special advisor on urban innovation of the European Commission. So as you can see, Professor Ratti's expertise and accomplishments are well aligned with our theme, and we are very much looking forward to his keynote this morning. Please join me in welcoming Carlo.
Thank you. Thank you. Thank you. Good morning, everybody. Great pleasure to be here with you today in your beautiful campus. So what I wanted to do today is share with you some of the work we're doing at MIT at Senseable City Lab on cities, and then I'll try to be a bit shorter than the time we have, so we can then have a discussion and exchange some ideas. But first of all, just a couple of thoughts about why we look at cities. Just 4 numbers about cities: 2, 50, 75, and 80. Cities are only 2% of the surface of the planet, of the crust of the planet, but they're 50%, actually a bit over 50% of the population now. There's 75% of energy consumption and 80% of CO2 emissions. So if we can do something to make our cities a bit more sustainable, that can be a big deal on the global scale. And well, what can we look at? Let's look at what's happening today, the convergence of the digital and physical world. If you look at this, that's an image that people used to be fascinated in the 1990s. The 1990s at the beginning of the mainstream digital and internet revolution, people thought that our lives would become increasingly virtual. So virtual that at the time, many thought that basically even cities might disappear. This is Gilder, an American writer, 1995, the same year when Nicholas Negroponte wrote Being Digital, saying we're headed for the death of cities. Cities are leftover baggage from the industrial era. What does this tell you? The first thing it tells you is never make predictions about the future, because no prediction could have been more wrong than this one. We know that cities have been thriving over the past decades. That's a picture from Tianjin in China. China this century might actually build more urban fabric than all of humanity ever built. We know that since 2008, half of the world's population lives in cities, and this number might swell to 5 billion by 2030. So what has happened, really, is that digital hasn't, quotes, killed physical space like Gilder and many other thoughts, but actually digital and physical are recombining. If you want, you could say that the internet is becoming Internet of Things, is entering the space of the city, the space we inhabit, and it's creating a new hybrid dimension in between bits and atoms with us in the middle. And that dimension is changing many dimensions of urban life. Now, that's what we're exploring. We're exploring, first of all, at Senseable City Lab at MIT. Also, we got a lab in Singapore. As you know, MIT has a research operation in Singapore. Also with our design office, it was mentioned before, and with some of the startups that are coming out of both, have been coming out of both over the past few years. Now, I framed today's presentation around some questions. And the reason is that, we had some of these questions, we discussed them with several people also here in the country. We recently had a visit from the team from NEOM, So, you know, but those are some of the questions that many mayors are concerned about, or many people dealing with urban issues today. And so the first is about how is mobility changing our cities? We know there's autonomy, autonomous vehicles. It can be, you know, cars, it can be drones, it can be boats. You know, how mobility is changing in cities. Then the second thing is about a lot of the urban fabric in cities is actually office spaces. And we know that's also changing a lot because of digitalization. A third point is about also retail. Retail means, you know, that today, thanks to e-commerce and so on, a lot of changes again are happening in cities. And ultimately, how all of this is going to change our experience of urban space. So that's our strategy today. And I want to start with you sharing some of the work we're doing about mobility. Starting with one of the oldest projects we did at MIT. This was over 10 years ago. We had just started the lab. It was shown at the Venice Biennale. It's a big exhibition where it's in Venice every couple of years, where, you know, all the world of architecture and design comes together for the exhibition. In that case, we had a pavilion. And in this pavilion, we did something that hadn't been done at the time. We looked at real-time data from a city, a lot of real-time data collected from millions of people, anonymized and aggregated data collected from cell phones and so on. Then we collected the data from, in this case, from the city of Rome. We sent the data to servers we set up at MIT. Then we use artificial intelligence in order to analyze the data. We visualize the data. And then we send back in real time the results to Venice. Now, and this hadn't been done at the time. So, you know, especially using the cell phone data from so many people. Over 10 years ago, you know, cell phones were still picking up. They were still growing. Cell phone penetration in different populations was still growing. And so it allows us to discover quite a few interesting things about the city as a living organism, something we couldn't see just before this kind of digital physical convergence we were talking about before. And I want to share with you just some of the visualizations from that summer. That was 2006, as I mentioned. It was an interesting summer because a few special events happened, including the final of the soccer World Cup. And it turns out, actually, that that was Italy and France playing. Italy won in the end. And look at what happened in the city of Rome that day. In this case, we're looking at cell phone data. Oops. Apologies. This was not expected. Hopefully, all the other movies are going to work. Looking at, but I'll play it from another side. What you see here is cell phone data from the city of Rome and collected from, again, from many people, from millions of people. And you see what happened during that particular day of the final of the World Cup. So I'll play it here, and then hopefully the others will all work fine. But what you see here is the city of Rome. You see the river, you see the Colosseum. That's before the match. You know, people playing here and there. People moving here and there. That's the afternoon, before the match still. In a moment, the match begins, silence, nobody speaks anymore. France scores, Italy scores, halftime, people make a quick call. And then a second time, end of normal time, first overtime, second overtime, a famous headbutt by Zidane. And in a moment, Italy wins. And you see, that night, everybody goes to celebrate up there at the top. The following day again, the winning team went back from Germany, went to meet the prime minister. And you see everybody going to the city center to greet and celebrate the winning team. And by the end of the day, people moved to a place down there. In the image you see in the lower part of the image called Circo Massimo. And that's a place where, since Roman times, people go and celebrate, and you see that peak at the end of the day. All right. Oops. So let's hope all the other slides will be okay. I'm pretty sure they will be okay. So today we can really see a city like this. We couldn't a few years ago. That's another visualization. In this case, what you're seeing is actually billions and billions of data points collected from Lisbon, again, describing mobility in the city. And the city like a living organism like you couldn't see before. Incidentally, that's a visualization done by Pedro Cruz from our lab at MIT. That was at MoMA, Museum of Modern Art in New York. But the data that is behind is very, very interesting in order to understand what's happening in our streets. And if you take the same data and you analyze it, you can find interesting things. So there's similar data in New York. Here you see taxis, pickups and drop-offs. Every dot is a pickup if it's a yellow dot, or a drop-off if it is a blue dot. What you see here is JFK Airport in New York. If you zoom out, JFK was down there. You see Manhattan and all of the boroughs. And then when you got this data, you can ask yourself different questions. For instance, you can ask yourself, well, today we like to share many things in our lives. We like to share apartments on Airbnb, couches, on couch surfing platforms. So, you know, how much we could share mobility in the city. Now, if you want to phrase it mathematically, you could say, imagine you want to take everybody to destination when they need to be there, give or take a small delta, a small delay that you can define, then what is the minimum number of vehicles that you need? Now, in order to solve the questions, you cannot do it with traditional methods. Simply, there's too much data. If you use big data, in this case, if you were to use linear programming, you know, you cannot solve it at this scale because of the sheer amount of data. So in this case, we developed a method based on network science to solve that minimum fleet problem. What you see here, you see these kind of shareability networks I was telling you about before, you know, how they densify if you tolerate a bigger delay. What you see on the two images, D and D, is how this kind of the amount of shareable trips increases if you can tolerate a bigger delay. And then if you look at the results are quite interesting that in New York, you could actually take everybody to destination when they need to be there, give or take this small delta, but with 40% less cars than what we have today. Now, two interesting things happened after we published the results. The first thing is, actually the results were published, there were a few releases of the results. We're still working on this data. There's some new papers coming out actually in a couple of weeks. But the first results came out before Uber launched Uber Pool. And at that point, Uber saw the results. They reached out. We started a collaboration with them. And as you might know, Uber Pool does exactly that, allows two people going more or less in the same direction to share mobility. Now, the other thing that was interesting is that when the paper was published, the New York Times reviewed it. And the comment in the New York Times was, well, you know, that's interesting mathematics. But you know what, in New Yorker, people don't want to share, you know, especially a car. It turns out that that's not the case. It turns out that now that we are using a lot of data from Uber, analyzing a lot of data with Uber Pool, then Uber Pool has been a big success. In San Francisco, over 50% of all trips every day actually happen by Uber Pool, which means two people going more or less in the same direction, sharing mobility, which means one less car on the road, which means less energy consumption, less congestion, less pollution, and so on. Now, the same thing that we saw for New York actually can happen in other cities. That's a more recent paper. We look at this kind of universal shareability laws, so trying to model mathematically what are the principles that allow us to share trips. And what you see here in this curve, it shows you that actually what we saw for New York, where the density of taxis is actually very, very high, also happens in most cities around the world. Now, this the first thing is about how we can share the vehicle itself, so how we can share the ride. But then what about sharing the car once at a time? And that is becoming also increasingly possible because the car is becoming a little bit like this. That's actually a piece of research where we look at all the sensors on a car and analyze them. And today in a car, you've got over 2,000 sensors. You see them here that record every possible thing about the driver. You know, they record every action in the car, if you're opening the windows, if you're pressing on the pedal, and so on. Everything about the city, about the temperature and so on. If it's raining or not, you got sensors for that. You know, and everything about the vehicle. So you know everything about the driver, the vehicle, and the city. And if you analyze it, the car becomes a very interesting sensing platform. So where you can do many exciting things, such as a microclimatic model using the car. You can look at human behavior. You can look at many other things. And as you all know, then, you know, little by little, we're adding additional sensors. So if you add those two little things over there, those two are two small LiDARs. What they do a three-dimensional scan of the city, such as this one. And then when you got this, if you feed this into an AI system, then the car drives itself. And that's not the future or the distant future. That's, you know, to a certain extent, the present. Yes, we're not yet at autonomy level 5, but, you know, that's really what's being tested today. In Singapore in particular, with the team in Singapore, we are working a lot with the government helping with this, one of the largest deployments of self-driving cars in the world, being tested in Singapore. Now, when this happens, then everything changes again. And the reason is that today the car is used on average 5% of the time, and 95% of the time it is parked somewhere. But with a self-driving car, the car can give you a lift in the morning when you go to your office, and then can give a lift to somebody else in your family or to anybody else in the city. So what you're doing, you're creating a new mobility system in between public and private transportation. And then, if you combine this, the sharing of the vehicle once at a time, with what I said before about the sharing of the ride itself, well, the combination of both could give you a city where theoretically you could actually satisfy the mobility demand with just a fraction of the vehicles we have today. I'm not saying this is going to happen. Other things might happen. Actually, if private vehicles or autonomous vehicles will cannibalize mass transportation, so we might end up in a different place. But still, theoretically, we could actually be much more efficient in the way we run our mobility infrastructure in cities. Now, that's as I say, this is kind of the present. If you think about the future, then when everything will be self-driving, other things might change. For instance, this. You're all familiar with this. It's a well-known traffic light. And traffic lights arrived on our roads when actually cars appeared on our roads. But if you got an intelligent system where every car knows where it is and where all the other cars are, then you need to stop anymore at the intersection. You can keep on going, just avoiding collisions, like this. Don't try it yet. I showed this video in Naples, and they told me, so what is new here? And I'm Italian, so I can make such jokes, but I had got corroborating evidence from my former Italian minister, who said, Minister Martino, that in Milan, traffic lights are instructions, in Rome, they're suggestions, in Naples, they are Christmas decorations. So again, if you look at an intersection seems something very simple, but mathematically can become quite complex, because you've got many different trajectories, and you've got different frequencies of arrival. And so if you look at this, in this case, we actually took queuing theory and tried to extend it to model mathematically the intersection. What you see in the next video is actually a real intersection in Singapore. Can we have also the sound from the video? Let me see. It's a real intersection in Singapore. To the left and to the right, you've got the same number of vehicles getting to the intersection. But actually, to the left, managed using the most sophisticated traffic light system we have today, and to the right, using a slot-based system, similar to what you have in airports. And look at the difference in terms of delay per car and cars waiting to the left and to the right. The interesting thing as well is that usually the intersection is the bottleneck, is the place where you've got two competing flows fighting for the same real estate. So actually, if you can fix the intersection problem, then automatically you fix many of the issues of the entire urban network. Now, all of this is about some of the research we're doing at the lab. Just one project we're doing in our design office to tell you how some of this is also making its way into design. And that's a tower in Singapore. It's under construction. It started like we broke ground a couple of months ago. And what do you see? Well, it's a tower in the middle. It has this kind of tropical forest that's like in a public space facing the city. But what I want to tell you about is more about the parking space. And today, when you build a tower, a skyscraper in most cities, you still need to provide a lot of parking space. But as I was telling you before, if you move to a self-driving paradigm, the number of parking spaces may actually be reduced in the city, as we were just saying, because the car doesn't need to be parked and keep on, running on the system. And so what we did here in this case was actually something quite simple, was for the parking space, and well, okay, today we need to provide it. But then first, let's put it above ground. If you put it underground, it would be very difficult to repurpose that infrastructure. And then let's make the distance between the floors a bit higher, the floor-to-ceiling height a bit higher. Let's do a structure that would allow transformation. Let's put the ramps outside, and let's leave holes for staircases in the middle, with the idea that the same space can be used for something else tomorrow. And I think that's a very important thing when we design cities, or as people sometimes say, smart cities today, is how can we actually future-proof them? How can we make sure that it will be compatible with different type of futures? And we don't know today's technology what it will lead to. It can lead actually to different outcomes. As we were saying before, we could run a city with less cars than what we have today. But actually, if things, are not controlled, we might end up cannibalizing public transportation, and then, we might end up with even more cars on our roads. So I think the important thing is how we can future-proof it and make what we build today compatible with different scenarios. Because the infrastructure we build today will last for like 50, 100, 200 years, while actually the life in the city might change much more rapidly. Now, another project also about autonomy, in this case, not in a special city, in the city of Amsterdam. And I say special because it's a beautiful city. It's a city where you don't have many streets in the city center, but you have a lot of canals. So we started around a year and a half ago working with the city of Amsterdam, and we said, well, what about autonomous boats? We call them rowboats. Well, what could you do with a rowboat? With a rowboat, you can use it in order to move things around, like this. In order to move people around, like this. You can use it to sense the water quality, the air quality, as you see on this video. But also think about using them almost like it's floating bricks or floating pixels. And then if you got an emergency or kind of a special event, you can create a structure in the city. You can self-assemble a structure in the city. Think about a temporary bridge. Think about a stage, a floating stage, or something else that you might use in the city. Which, of course, is nothing new. That's what the city of Venice has been doing for a long time. During a special day called the Festa del Redentore, all of the gondolas come together to create a temporary bridge. But I think that's sometimes the interesting thing about modern technologies, as Paul Valéry once said, it is about, they help us to do old things, but in a new way. So we're working on this now for a year and a half. You see here we're designing the boats a little bit like drones. The great thing about drones is that you got, 4 engines. They're all the same. They're easy to control. So we're trying with 4 engines placed like this, or 4 water jets like this. What you see here is the first prototype is 1:4 scale. So the final one will be 4 times bigger. As we speak, there's actually new models being made. They're 1:2, so they're twice the size of this. What you see here is this being tested on the canals in Amsterdam. You see it's very easy to control. It's symmetrical. It can also move laterally. We told the mayor, even if the project is not successful, in the worst case, we'll open a toy company because everybody seems to have so much fun playing with these things on the canals. You see here, actually, this being tested at MIT. That's actually, we are testing all of the control system. This is actually the swimming pool at MIT. What you see here, on the curve, you see the difference between what we're trying to do, like in that square, in actually the real trajectories. There is the self-driving boat, from one side, it's easier than a self-driving car for 2 reasons. The first reason is that the complexity of the environment is usually less, so you got water and a few other boats. And also the speed is lower. So when you got lower speed, it's much easier to analyze it. But for something, it's more difficult, and the reason is that if you got a car, you know the response of the vehicle because it's pretty much stable. But if you got the boat, the center of gravity and everything else keeps on changing. You got people on the boat, they sit on one side, on the other side, so the response of the boat keeps on changing, and you need to constantly recalculate it. So that's some of the work we are doing at the moment in the lab. And also we are using them for different things in Amsterdam. For instance, Amsterdam has systems to go on little boats, to go on the canals and clean the canals. So one of the first prototypes we'll deploy in the next few months is an autonomous system like this that will move around and actually collect plastic bottles and other things and clean the canals with this. So move around a bit like a small Pac-Man, and then collect the stuff and then put it there, and then it can be used in order, again, to take all what ends up on the canals. Well, as we're talking about autonomies, I wanted to share with you also some other thoughts. The first is about this. And you probably have seen a lot of people writing and saying that tomorrow's cities will be filled with this type of machines, with quadcopters, and we'll move in cities with this. Well, I do not think that's going to be the case. And I think we'll use drones for many things. They're going to be very exciting, very useful, especially small drones for sensing the city and so on. But if you think about a big drone, you know, that's a different story. And technology might change, but technology cannot change physics. And physics means that if you want to take a mass, like the mass of a human body, and put it up in there, then in mid-air, what you need is a lot of energy, and then you generate a lot of noise, and then you generate a lot of downward wind in order just to get the thrust to be up there in the city, in the sky. And so, you know, that creates a lot of disturbance. If you think about New York, about Manhattan, you got helicopters, you got a helipad and a few helipads. And if you take the helipad in lower Manhattan, there's a few tens of flights every hour taking off. But just with a few tens of flights every hour, everybody complains in the city, in the neighborhood, and so on. But if you wanted to have an impact on the mobility of Manhattan, you don't need tens of flights every hour. You need tens of thousands of flights every hour. So I don't think that will ever be possible with, you know, with drones or helicopters. But as I was saying, we can use them for many other things. We can use them, first of all, outside of the city where there's no infrastructure. We can use them for fun. That's a fun project we're doing with drones, you know, using drones to spray paint onto the wall and to do collaborative graffiti in the city. Or we've been using drones on the MIT campus in order to help people who get lost. You know, the MIT campus is quite difficult to navigate. I know some of you are from MIT. I met you before. You know, it's a campus that was built by engineers. Every building has a number. For instance, I'm in the place 9250. And sometimes visitors have to go to building 36-235. And, you know, and a lot of people on the way, you know, really get lost. So we developed this system in order to help them, and in particular, to help Harvard students. Here's the video.
Welcome to MIT. Where would you like to go? Follow me, please. The Computer Science and Artificial Intelligence Lab is the largest research lab at MIT.
To your right, the Media Lab. To your left, the Data Center.
Follow me, please. Approaching your destination.
You have arrived. Welcome to Senseable City Lab.
Goodbye.
All right. Thank you. All right, so that was about, you know, mobility, just a few thoughts about mobility. Now, a few other things about, you know, we set up office spaces. And as we were saying before, digital is changing a lot the way we work. That's an op-ed in the Harvard Business Review. We did just recently, you know, looking at the changes in the way we work today and in office spaces. And actually, the title they gave was, if work is digital, why do we still go to the office? Now, I believe there's still a reason to go to the office, but it's a different reason than the reason we might have seen 10 or 20 years ago. And in order to look at that, it might be good to go back to the principles of city making. This guy is Le Corbusier, one of the main architects of the 20th century. And together with a group called SIAM in the 1930s, what they did, you know, they wrote something called the Charte d'Athènes, the Athens Charter. In the Athens Charter, they theorized a city where everything had to be divided. So a place for living, a place for dwelling, a place for recreation, and then connections between all these places. But if you do that, then you end up with a city like what you see there to the left, so a city where everything is separated, and then you generate a lot of traffic between the different parts. And if everything is separated, it means you've got a place for sleeping, for instance, the district, the residential district, which is used only for part of the day, and the place for working is used only for part of the day. So you multiply space, and you use it just for part of the time. And so it's no surprise that since the 1950s and 60s, all across the planet, including in the United States, Jane Jacobs in particular in the United States, thought about mixed-use developments, how we can actually combine different functions, put them together in the city, and create a much richer district that actually uses space in a more efficient way. But we believe that today things are changing again. And what you see there to the right is a little bit this idea that the space, the way we use space is more flexible because of technology today, and hence it helps us not only to juxtapose different functions one next to the other, but also to use the same space for different functions over time. So something that could actually change the transition between public and private and the very structure of the buildings we inhabit. Now, in order to look at this in more detail, I want to share with you some research we've been doing at the MIT campus. So what you see is Boston, downtown. By the way, Boston is a very green city. Apologies, it looks a bit like post-nuke, but it's a winter picture. But you see all the parks, and it's a very green city. Downtown, MIT campus, like a small city inside the city. Harvard up there, don't bother. And MIT was one of the first places to be totally covered by Wi-Fi in the early 2000s. And through that, we saw a big change. People used to work, as you see there, to the left, and now tend to work, as you see there, to the right. Now, this picture is a bit extreme. What you see there to the left is the most depressing computer room I could find. And to the right is a beautiful sunny day. I need to tell you, last week it was not the same. It was rainy and miserable. But you get a sense, we used to work like this. Incidentally, this is Jacques Tati, the French filmmaker, making fun of cubicles. And now, today, we tend to work like this. So our idea was, well, what's the difference between the two? The difference is just technology. Because before, we were chained to a desk. Maybe we had a desktop computer. We couldn't really move. And now we're more flexible. So that's how we can work in a place like this. So what about going and measuring these changes through technology itself? So what we did, we started monitoring the Wi-Fi network on the MIT campus. And then you see here all the access points from the Wi-Fi network. Then you can, for instance, look at where people are in the course of the day. Again, anonymized and aggregated data. It tells you how much activity, how many people you have in different parts of the campus. You see there in the morning, people waking up from the dorms, moving to the center of the campus, and so on. If you look at the overall signature at MIT, it looks a little bit like this. If you look at the curve at the top, you see that's a Monday, Tuesday. So Monday morning, 9 a.m., a lot of people arrive to campus. A few people leave at 5 p.m. You see it over there. Most people keep on working till late at night, 8, 9, 10, 11 p.m. Even in the middle of the night, you got a lot of activity. And the same thing happens on Monday, on Tuesday, on Wednesday, on Thursday. Not on Friday, where like all over the world, activity slips away very quickly in the afternoon. And then Saturday and Sunday are almost like two normal days. You remove the 9 to 5 people, you got the same baseline almost. With something quite interesting, every Sunday night, you can see you got a little dent that's between 9 and 10 p.m. And that's when everybody realizes and say, oh my God, tomorrow is Monday again. And you remember all the things you haven't finished before the beginning of the new week, so you go back to your computer. Now, if you look at this is the overall signature, but you can have the same signature for every space on the MIT campus. So for every room, you can actually look at this, and you can analyze it, and then again, you can do analytics on it. Here you see frequencies, here you see different type of clustering. And if you do the clustering, you find something like this. There's a few papers, if you're interested, there on our website that explain the methodology. But when you look at this, it's a bit like what I was saying before, is the fact probably this map a few decades ago would have had different colors, very, very separated. Every space, a clear function, and that function wasn't changing over time. And today you get actually this different mode of using space, which is with flexibility, both between one space and what is next to it, and also how we use space over time. So this kind of blurry of functions we were saying before. Now, if you think about this is about how people interact in physical space. But think about what is a great university, like here, like on the MIT campus, like many other places around the world. So, well, if you want to think about it mathematically, it's nothing else than a place that brings people together in physical space, allows people to interact in digital space, through email and so on, and then allows us to do something together, to make sure that together we can achieve more than each of us individually, to make sure that the total is more than the sum of the individual parts. And so what we are doing now, it's still in progress research, but it's actually here you see the physical interaction, but we're also looking at productivity. So what are we doing together? If you look at the universities, usually papers and patents. So you see here where papers and patents have been produced at MIT over the past 10 years. What you see, you can also look at the different communities that produce paper and patents, and also the digital interactions. So when you combine all of that, we think there's something very, very interesting to better understand kind of this secret sauce, which is behind every organization and behind the culture of every organization and behind the space making of the organization, to go and measure if the space that we inhabit actually is conducive to what we are doing together in digital space in order to, in this case, do papers and patents. So they're still in progress, but there's something we're quite excited about looking at these kind of three interactions and how they can help us to do to achieve the mission of our institutions. We're using this as well in our design office to design real places. These are some of the largest co-working spaces in Europe. This opened in Milan last year. This is a place in America where we've been using a lot of, the key point is about openness, is about opening up the building in order to allow more interaction between people. If we just need to do something on our own, we don't need to go to an office. We can do it from home, from a lounge, from an airplane, it doesn't matter. But actually, if you go to an office, the reason is how we can better interact with each other, how we can create that serendipity that allows new ideas to be generated. So in this case, also outdoor spaces. I think your beautiful campus, I think, is also conducive to that, to being outdoor for a good chunk of the year and being able to do things outside and meet with other people. That's a building we just finished a few months ago. We're actually also the building, because the building knows occupancy, as we saw on the MIT campus, then the building responds to it. So heating, lighting, and cooling all respond dynamically to people. People can have their own personalized climate following them through the building, just because then they can set it as they prefer. Those were some of the initial renderings, and I'll tell you a bit more about the story of this building. This was one of the first reviews from a few months ago. But I'll tell you a bit more about this building and how we ended up with this idea. This building is a building in Italy. It has a lot of symbolic value in Italy because it's the place where Fiat was started. And Fiat was the largest conglomerate in the 20th century. Today is the company that's behind also Chrysler, Jeep, Ferrari, The Economist. Well, the holding company or the family who founded Fiat is behind all of these companies. And this was the little house where everything started. It's a building that was built over 100 years ago. And then this was the beginning. And then in the 1950s, the building was expanded. And actually at the time, a group of architects went to the United States in order to look at state-of-the-art offices from the 50s. It was expanded. It became the family foundation. You see here what was added. Both of the buildings, the old building and the 1950s one, are listed today. And buildings of the 50s looked pretty much like this. That was state-of-the-art in the 50s. As we saw before, it was about, almost creating separated, segregated spaces where people had to execute tasks. But today, most of those tasks have disappeared. They can be done by artificial intelligence, by robotics, and so on. So the idea is how can we create a different working place? And the way we did it was, first of all, by opening up to the city, opening the building to the city by adding these kind of volumes, opening the building internally, between the different floors, making sure that people on different floors would also interact. So both with the existing staircase that had been closed down in the 50s, opening it up again, also in creating new porosity in the 1950s building, and also opening up to nature. As humans, we've been living with nature for thousands of years, is what my colleague at Harvard would call, E.O. Wilson would call biophilia. It's part of what is coded inside us. And then only in the past few hundred years, we actually locked ourselves into buildings that sometimes today look like fish tanks. And I think, how we can go back and, thanks to the new flexibility we have, we can go back to enjoying nature and living and working in nature. Here you see some of the first picture of the building completed. There's still no furniture here. That's an orchard where actually people can go and enjoy the landscape. Also, you see here the offices to the left and how they open up. So the office is indoor and outdoor. Outdoor, you can also have a meeting. You can have a small conference. And, you can go on your own and work on your laptop. So the idea of creating this porosity between inside and outside. You see the places inside, these kind of systems that detect occupancy and then will create climate according to your preferences, heating, lighting, and cooling, as I was saying before, following you through the building. Here you see some of the working spaces as they were finished and also inhabited here, starting to be inhabited. Also, this kind of porosity between different levels, in this case, creating this kind of nets in order to allow people to keep on working, but still to create visual and acoustic connections between the floors. Again, very important, not just separating between one level and the other one, but actually trying to connect them. Also, the old historic buildings, trying to create offices that would not be totally segregated, and open up the staircases, as I told you before, back to the light and back, to communication between different heights. What you see, by the way, incidentally, over there is a sculpture that was done by Olaf Eliasson, and what we try to do was actually, in this case, to allow connection, in terms of visual connection between two sides of the building, but here we didn't want to have direct lines of sight because of privacy. And so what it does is almost like a kaleidoscopic wall, as you see here, that actually allows you to see from one side to the other one. You see light, you see movement. It transmits almost everything, but it doesn't transmit a direct line of sight between the two sides of the building. And, art is very important. As we were saying before, it's about, the office is a place where you can stumble on to somebody else and start talking, and new ideas and serendipity emerge. And art is very important in order to promote that and foster that. So I think there's art throughout the building as part of really why is how it can help us to start new conversations with the people we share spaces with. All right. So that was about office spaces. Another important part of cities is also all the infrastructure for retail. There's a huge chunk of the real estate we got in our cities, and that's changing a lot. It's changing. That's a recent article, according to a study by Credit Suisse, 25% of US shopping malls could close in the next few years. And, there's a huge amount of real estate in our cities. And what's the reason? Well, again, the reason is about digitization, digital and physical, is about e-commerce. As you all know, Amazon bought Whole Foods in the United States. It's about new things such as Instacart, that's somebody going shopping for you and taking, shopping and then, taking what you bought to straight to your home and just shopping for you very, very quickly, so you can order it at 5 p.m. By 7 p.m. you have all the groceries at home. And so I think, again, in this case, we're going to digitize a lot of things in our cities, but probably we're not going to digitize things that have a very unique experience. And we explored this in this project that was at Milan Expo. As you know, the Expo, the World's Fair, 2010 was in Shanghai, 2015 was in Milan, 2020 will be in Dubai, here in the region. And in this case, we were fortunate enough to do 2 pavilions. And one of the 2 pavilions was what they call the Future Food District. And the theme of the Expo was about feeding the planet. And so it was about food, about production of food, about distribution of food, and about transformation of food, eating, and so on. And in this case, they gave us as a topic, say, well, could you try to design a future supermarket with the idea that this would be both a thematic pavilion and also a real supermarket where people could shop at Expo. And I need to tell you, I take no responsibility. The building is there to the left for the building on the outside that was given to us, that kind of shoebox. But we could do anything we wanted inside. And we knew what we did not want to do. We didn't want to do this. It's a beautiful picture by Andreas Gursky, but it's kind of an alienating picture of the supermarket of the 20th century. Our inspiration was this quote by Italo Calvino, an Italian writer. Some of you might have read Invisible Cities. It's very popular, especially in architecture schools. But in this case, it's from a character called Mr. Palomar. Mr. Palomar is a character who's a little bit aloof, a bit provincial, and one day goes to Paris and goes into a cheese shop and looking at every piece of cheese and think about the stories behind every piece of cheese. And little by little, the shop for him becomes like a museum, like the Louvre. Calvino says the shop is a museum. Mr. Palomar, visiting it, feels as he does in the Louvre, behind every displayed object, the presence of the civilization that's given it form and takes form from it. This idea of things, objects, products telling their stories is not new. Many people try to address it. For instance, Tesco, a big supermarket chain based in the UK, but active all over the world, tried this in Seoul. It was actually in the subway. You see there's a train stopping there. And the idea was, well, you take your phone, you scan a product, you learn about the product, and then you can order it. But if you look at this, it's a bit alienating as well. It's about yourself with a screen in front of you and another screen behind, and no human interaction. Our idea was, well, can you actually use technology in order to do something that resembles more like this? And if you look at this, in this painting, look at the richness of interactions between people and products, on people and people through products in a traditional market. And the way we did it was, first of all, by putting everything on tables. You know, a table is a beautiful interface. For thousands of years, we've been using tables to eat together, to share things, to sell things. And on top of the table, we put a lot of Kinect sensors. As you all know, the Kinect is almost like a miniature, a small and simplified, a miniature kind of 3D scanner. And so the idea is that, you know, if you approach a table, automatically the Kinect will detect you, will look at what will detect what you're looking at, and then will display information about the product. So this was one of the initial sketches, the idea that if you want to buy an apple, you can buy it like today in 1 second. But if you want to actually, if you want to learn a bit more about it, if you have 3 seconds, then you can see where it's coming from and some basic information. If you got 10 seconds, you can even see the orchard, the video of the orchard from where the apple is coming from. And all of that automatically, you don't need to do anything, you just, you know, approach the apple, touch the apple, and that information will seamlessly appear. Now, we designed the whole thing like a theater. We like the idea that, you know, you would have from the top, you would see all the different products, and you see it here, you know, in one go, you would actually see all of them, with the different layers of information, the physical layer, but also a digital layer of augmented information about the products, and also the top aggregated digital information about all what's happening in real time. Now here we see the supermarket built. It actually won a number of design prizes and was one of the most visited pavilions at the expo. You see the different products. Here you see the different layers, digital, you know, the different layers, one next to the other. Here you see people playing with products. Something interesting was kids loved it. They would jump from one product to the other one and look at this accordion of information popping up. You know, that's, for me, the interesting thing was that there's a lot of technology, but if you do the right interface, if you combine interfaces with physical objects, then, you know, people don't need to think about the technology behind it. You can just do as you do in a normal supermarket, approach a product, and then the information will come seamlessly. So somehow it becomes a tangible way, a tangible user interface in order to in this case, to know more about the things we buy, and hopefully to promote more informed consumption. And again, if you got just a few seconds, the information you can get is this, about nutritional values or carbon footprint, but the more you play with something, the more you learn about it. And here's a little video about the experience inside. Sorry, here is actually a real supermarket being built in Milan recently, so using the same technology. So again, you know, this technology is now making it into the real world, and in this case, you know, simplified, but actually into a real supermarket. Or, you know, this is about the experience in this case, about products and stories behind products. We've also been doing a bit of work with Italy. It has been very popular in New York, since it's in the US, since it's open in New York. Now it's also in Boston, Los Angeles, in Chicago. And here with the latest format, we've actually been looking also at bringing back production inside the supermarket. Within production is going to be very, very important in tomorrow's cities. We're discussing this, by the way, also with the team at NEOM, the new city being built here in Saudi, a bit how production can also, is again part of biofuel. It's not only about energy, it's not only about having healthier food. You can produce in a place without, you know, in a controlled environment, without pesticides and so on. But it's also about connecting us with nature, as we said before, about this kind of biophilia. So in this case, it's just open recently. It's about where everybody can produce. You know, you can plant, and then you can follow. As you're moving through space, you see what people have planted before. So it's almost like moving through time. As you're following this path, you're looking at what people have planted a week or 2 weeks before. So you see all of that. And then you can follow that also digitally. So it becomes, again, a way to bring production inside the supermarket and learn about it, and then you can actually eat what you produce or what other people have planted, and again, follow it and learn about this. So again, you know, what will probably remain tomorrow, I believe, is that experiential side, the thing that cannot be digitized. Things that doesn't have an experience, all the products that don't have an experience probably will just get by shouting to Alexa or to Siri, you know, get more X. But the things where there's an experience, those are the things that I think will remain in the city, and probably we need to design new spaces for them. And talking about experience, I want to finish with one project. That's a project we also did at the Expo. It was a previous Expo. It was in Spain, in the city of Zaragoza. And there the World's Fair had a very special topic, and it was water. And then the mayor of the city came to us and said, well, how could you use water today in a different way, in a more precise way? Again, thanks to digital technologies. And one of the first ideas that came up was the following one. If you look at that pipe has many tabs, opening and closing controlled by a computer, and so it allows you to create like a digital water wall. So you can have like a living water wall where you can show images or text or patterns. Also, if you approach it, like you see there, it opens up to let you in. Now, the mayor liked the idea, so we got the commission to design the building at the entrance of the Expo. We call the building Digital Water Pavilion. All of the walls are made of water, again, where you can show text or images or patterns. No doors or windows, but when you approach the building opens up to let you in. When you're inside, also, all of the walls expand and shrink based on how many people you have. The roof is also covered with a thin layer of water. And if you got too much wind, you can lower the roof to minimize splashing. Or at the end of the day, you can close the building and the whole architecture disappears. Hopefully without anybody underneath. We got sensors for that as well. So we had fun doing the video. We didn't really think that they would build it. Then what happened is, was mentioned before, is like 9 months before the opening, Time Magazine listed the building into among the best inventions of the year. So we got a commission to do it in a rush. At the end, you see here the building before the opening. I like this picture. You see that guy had a trolley, was actually going to the station. The station is next door. I think he missed his train because he stopped there, you know, for a while and kept asking, you know, what the hell is happening here? He couldn't figure out what was going on. Here you see actually digital and physical pixels. So you see pixels made of water and also projections on the water, so the combination of both. Here it was myself trying not to get wet. And so I was testing all of the sensors and how they open up the curtains, the water curtains, when you approach the building. And I should tell you now what happened one night when all of the sensors stopped working. And that night we were terrified because the building would keep on doing its own crazy things like cats and holes and images and so on, but without responding to people anymore. But that night ended up being one of the most fun nights ever. That night, thousands of kids from all over the city went to the building to play a new game. Not anymore a building that opens up when you approach it, but a building that you need to engage like this. And for us, it was an important lesson because, you know, as architects, engineers, we always think that we know how people will use the stuff we design. But reality, and especially human reality, and especially human reality when it interacts with this kind of new hybrid digital physical world, well, is always a surprise. In this case, it was a good surprise. Thank you. And I kept the presentation a bit shorter, so so we have a bit of time for discussions. If there's any questions or ideas, thoughts, challenges, feel free to raise your hands. Yes.
Hi, very interesting presentation. My background is air quality, air pollution. I just wonder, because my area just during many years research on the human exposure to atmospheric pollutants, I was quite surprised to see the microenvironment assessment, how people behave inside indoor environments, outdoor environments. Is there any correlation in your work with another layer would be air quality, indoor air quality, human exposure?
Totally. Actually, while you were talking, I just was opening our website, and I didn't present it today, but actually I'll show you here in this project. It's a project from a couple of years ago. We call it urban exposures. Here we looked at a very important problem. When you look at air quality today, it's usually just something static. So people will measure, have a few sensors in the city, measure air quality, but regardless of individual exposure. So what you want to measure, if you are interested in public health, is actually individual exposure. And so here what we've been doing is a couple of papers. One actually just came out a few months ago. The first one is from a couple of years ago, is look at using all the movement of the population, as we saw before, using cell phone data, in order to better understand exposure. And what you see is that the policies that the city could put in place are not the one you might put in place today with static data, but the policies that come out of the intersection of mobility data with exposure could be quite different. And so that's actually looking at measuring not only pollution levels in the city, and I mean static, not over time, but static over space, but actually combining that with the mobility of the population. Also, we have been working on this other project. Oops. Sorry. Let me open it here, it's easier. We have been working on this other project. Oops. That we call City Scanner. And that's something, again, you can find a website. This is something we're working on right now. And in this case, we're actually, again, one of the traditional problems with air quality is that you got a few monitoring stations that are usually very, very expensive, and you only get data in a few points in the city. But again, there's a lot of variability just between one side of the road to another side of the road. And, that measurement is not necessarily representative of a larger part of the city and the population. And so what we've been doing here with what we call City Scanner, it's in Cambridge, we've been developing this kind of a small sensor package that we put on garbage trucks. And then we use that in order to keep on scanning the city. And we're discovering interesting things. For instance, if you just use 3 garbage trucks in Cambridge, Cambridge is a city of over 100,000 people, then only with those trucks, you actually scan the whole city and every road in the city at least once a week. You get very, very good data, and you constantly collect it and so on. So again, this idea again of using ubiquitous computing in order to apply to sensing becomes very interesting. And again, you can apply it to drones as well, and to many other vehicles or fleets, to taxis in this case. But for us, interesting was, again, we're doing some mathematical modeling, looking at the mobility patterns of the city and how well you can cover it. And it turns out with much less investment, you can actually use moving sensors and get better information about the city. So I want to say that air quality is, for us, is very, very exciting topic. Actually, we are working. We got a couple of people working on this, and delighted to explore also collaborations. What we saw at the beginning, this convergence of digital and physical, of Internet of Things, I believe is going to transform it quite significantly in the next few years, and that's exciting. Yes.
Hello, thank you for your talk. You were showing very nice animations about traffic lights, so city without traffic lights. How about like dynamic traffic light systems which implement like computer vision? How advanced they are now?
Yeah, thanks for asking it. Well, what I showed you in that video, I will not play it again, but in that video it was an intersection in Singapore, a real one. Same number of cars getting to the intersection to the left and to the right, but to the left it was actually with the most sophisticated dynamic traffic light system we have today. So what you see to the left was actually using the most sophisticated system, which uses cameras, know how many cars arrive, and adjust accordingly. And to the right, you had this kind of slot-based system. And the reason a slot-based system works better is that it works a little bit like a roundabout. You can really use space better. The problem of a roundabout is usually you cannot use a roundabout in a dense city. You will never be able to do roundabouts at every intersection in Manhattan. And so, but what you saw there to the left was exactly what you're saying, the most sophisticated intelligent traffic light system you can think about today, using cameras in order to see how many cars you have waiting. Cameras or loop detectors, doesn't matter, but you know the number of cars. Thanks. There's a couple of hands there, yeah.
Yeah, so thank you for the presentation. It was very interesting. I was wondering about transportation. You kind of talked about the possibility that public transportation would kind of be eroded as we have more autonomous vehicles. What about the possibility of maybe kind of mingling those two together, maybe building a new system that would be kind of more like public transportation but using individual vehicles or something like this?
Look, I think, it's a great question. And I think we're going to see a lot of that. So let me tell you, the first thing is about the same technology can lead into two totally different directions, as we were saying before. So yes, some of the papers, some of the numbers that you find in the McKinsey report and so on came from some of the papers we did. You find them on our website, where we estimated kind of the lower bound. In theoretically, we could run Jeddah or New York or Singapore or Milan, a bigger city or a smaller city, theoretically with 20% of the cars we have today. At the same time, as we said before, if today, let me elaborate a bit on that. So today, an Uber in the United States, the cost of an Uber is something around $2.2 per mile. And if you go to a self-driving car, that number is expected to fall to something between 30 to 60 cents per mile. Now, if you go 30 to 60 cents per mile, today is less than the cost of the subway in New York or the underground in London. Depends how you count it. Usually with the subway you can take a longer trip, but it can be less than that. And at that point, everybody clearly would want to have like a private vehicle collecting them at home and taking them to their destination. But if that were to happen, so if basically self-driving cars were to cannibalize mass transportation, then then our cities would end up with even more cars than what we have today. And actually, that would not be possible. There's simply not enough space. So those are kind of the same technology could lead to two totally different scenarios. And the difference between the two scenarios will depend on the regulations we put in place. For instance, about something interesting would be about taxation. With self-driving cars, a lot of taxes will disappear. Today, governments make a lot of money, especially in Europe and in the United States, with taxes on oil, with taxes on vehicles themselves, also with parking meters. So all of that might actually evaporate, disappear. And so the question is, what type of alternative taxation system our government is going to put in place? For instance, if you think about road pricing, that could actually force people or increase the cost per mile, and then people again will reduce this kind of shift. Or you can also think about taxes on one side in doing what Germany is proposing right now, has been discussing over the past few weeks about making public transportation completely free for everybody. So there could be another way to incentivize people to keep using mass transportation. But again, the point is the same technology can lead in different directions. Now, what you're saying is very interesting as well, because I think we will also see a new generation of form factors in terms of cars. And the first thing that's very simple is that, in the 20th century, why did we have a 5-seater when the average occupancy is 1.6 people per car? And so we're using all this kind of empty space around ourselves. We're moving, tons with our body. We weigh 100 kilos, we're moving 10 times of that. One person in the car, or 1.6 people in the persons in the car, and we have a lot of empty space. Why do we do that? Well, because in the 20th century, if the only way was to own the car, and then if you own the car, the average family is 4 to 5 people, and then you want to plan for the peak. And the peak is when you go on holidays a few times a year and so on, and then you need to have a 5-seater. And then, but most of the year you will use it just with 1 or 2 people inside. Now, if you move to mobility on demand, which is what's going to happen with self-driving, what we've been discussing before, then, at that point, it doesn't matter. You don't need to plan for the peak anymore. So it means that most of the time, you can really just have a 1-seater or 2-seater. So I think we'll see a lot of smaller vehicles. And then the other thing I think we will see more is something which is approaching public transportation from the other end. So imagine like a minivan or a minibus that actually will do point-to-point, or leave you maybe like 50 meters from home, the latest Uber pool system, or, by different, or Via in New York. They don't take you exactly to your destination. You might walk a couple of minutes, but it's totally fine. So think about a minivan that does it, and if you look at that, it's still much faster than today's public transportation. So instead of taking the bus, you go to the bus stop, and then you take the bus, and then you wait for the bus, and then you go to another bus stop, and then you walk, maybe you take another bus line, and then you get to the final bus stop. Instead of doing that, you have still kind of point-to-point, or close to your origin, close to your destination, And yes, you need to wait a little bit because you don't take the shortest path. You need to drop people on the way, but it's still a very interesting mobility model. So I think we'll see also a lot of minivans and minibuses kind of form factor emerging. And then there's also thoughts, as I think probably you were referring to that as well, of thinking about can you have smaller capsules and they combine and they create almost like a bus. That's also interesting. The density of people you can put in that is not as high. If you look at I didn't show it today, there's a beautiful image you can find on the internet that people use often. It shows you the amount of road space you use with different modes of transportation. If you've got 100 people, if you put them in car, they use this much. If you put them in buses, they use this much. If you put it in the subway, they use this much. And the reason is that in the subway, we're all packed next to each other. We're standing most of the time, when it's very full. So again, we'll see a lot of this probably will not be as efficient as mass transportation today. I don't think we'll be able to keep Paris moving without the density that the metro, today the metro or the RER system provides. But I think certainly we can approach that with new mobility systems on the ground. So I think we'll see really a spectrum of different options and also a lot of new systems. Think about the Chinese bikes, the OFO bike and so on. There are very simple technologies applied to bike that allows dockless bike sharing systems, and it's been very popular. So I think we'll see a lot of mutations in mobility. Yes. But anyway, I spoke too much. Yes, last question.
Thanks for a very interesting talk. I wonder if you can maybe address the question related to the affordability of living in cities and how this technology may address that. Like you compare Sydney, San Francisco, London. Yeah. It's too expensive to live there. Yeah. So how are these new technologies and new advances going to change that?
I think you're totally right. I think affordability, I think, will change. Has to change in the next few years because it has become impossible to live in some of the cities you mentioned. I think on the one hand, I think we might see a correction in real estate prices. That will certainly make it more affordable. If you look, there's a few famous indices in economics that look at the income and real estate prices, and the two have to be correlated. You cannot have incomes here and real estate prices going up. And so when they go up too much, then they will certainly correct at one point because people need to work a certain number of years to buy an apartment, to pay for a mortgage, and so that cannot spin out of control. So this will be part of the story, but that's more on the price side, and also that's not going to be the same thing all over the world. But in some cities, I think we'll see a correction for sure. And actually, in some cities, we're already seeing it. In some of the big cities you mentioned, in some of them, we've already seen a little bit of correction. The interesting thing about the technology side is that the city of the 20th century, we saw it for mobility, was a city where you had a lot of infrastructure that you had to plan for peak. But then most of the time, it will not be used that much. But then you had to plan it for peak, and then it would be empty the rest of the time. And we talked about cars a moment ago, but the same applies to our buildings as well. And you think about something like Airbnb, what it does, it magically created the equivalent of one of the largest hotel chains on the planet, just without moving a brick, just by using spare capacity. So I think if we're able to use better spare capacity in our cities, that's going to make it more affordable. And a lot of the new experiments happening today in, say, co-living, they're based on the same principle. Now, what is the point? You have a big living room where you can have a dinner with, say, 12 people. But then you have the dinner once a month. And then the rest of the time, dining room, not living room. And then the rest of the time, the dining room is totally empty. So why not thinking about a system? And again, digital enables it because then you can have an app for booking a communal dining room. And when you want to have your dinner with 10 or 15 people, then you can just go inside the same building. You got a beautiful space. Maybe the top floor is better, nicer than the one you would have in your apartment, but you share it with other people. So you're using space better. And the same is what I showed you before about the co-working spaces. The interesting thing, if you think about a few years ago, the amount of square meters per person in an office was something around 15 square meters, 150 square foot per person. And today with co-working spaces, you go down to 5 or 6 square meters per person, which is 50 to 60 square foot per person, which again, it means that you're using a better way space, and that is going to make it more affordable. The reason is that in the past, everybody had their own private office, and even if most of the time you might have been in a meeting room, outside of the office, maybe on a conference, and then you still had a space that was empty. And in a co-working model, you actually share the space with other people. So I think, the second part of affordability is how digital platforms can help us to use space better. And if you use space better, it means less square meters or square foot per person, and hence it means more affordability. Yeah. Yes.
Thank you very much, Carlo. I think this is, with this question, we came to the conclusion of our keynote lecture. It's really been a pleasure having you over, and thank you very much for coming today.
Thanks a lot. It was really a pleasure. It was really a pleasure to be here today and also to enjoy your beautiful campus. If you're on the MIT campus, do come and visit us. If you get lost, we'll send you a drone to guide you through the campus. And in any case, let's keep in touch. Thank you. Thanks.